Have you ever driven past an oil refinery and just stared at that chaotic maze of pipes? It looks totally random, right? A complete mess. Well, what if I told you that every single piece of that puzzle is placed with life or death precision? Today, we're going to pull back the curtain on the hidden blueprint and see how to design a chemical plant from the ground up.
And this quote right here, it just nails it. This is from an engineering standard, and it gets to the heart of the matter. Plant design isn't just about making things fit. It's about preventing disaster. It's about making sure things don't go boom. Every single decision is a calculated move to control risk.
So here's our game plan. We're going to start with the big picture, kind of like a 30,000-foot view, and zoom in. We'll start with how the entire site gets laid out. Then we'll look at the arteries connecting everything. We'll dive right into the heart of a process unit. And then, finally, we'll see how engineers design for the absolute worst-case scenario. Let's get into it.
Okay, so imagine you've got this huge, empty plot of land. Where do you even begin? Well, you start just like you would with a brand new city. You create zones. I mean, you wouldn't build a school right next to a noisy factory, would you? It's the exact same idea here. You don't put the office building right next to a high-pressure reactor.
This very first step is called blocking, and it happens before a single pipe is even ordered. Engineers literally carve up the site into distinct zones. You'll have your main processing areas, that's where all the chemistry happens, then separate spots for storage, a whole utility area for power and water, and of course, an administrative zone for the offices and control rooms.
And what's wild is how much the natural world plays into the super high-tech design. Engineers have to think about which way the wind usually blows, the natural slope of the land, even what kind of soil they're building on. You see, they're not trying to fight nature, they're trying to work with it to make everything safer and more efficient. This is a perfect example of what I'm talking about. It's one of the most fundamental, absolute golden rules of plant design. You figure out which way the wind blows most of the time, and you put your ignition sources, your furnaces and heaters, upwind. Why? So if there's ever a flammable gas leak, the wind carries it away from the open flame, not straight into it. So simple, so smart, and completely non-negotiable. All right, so our zones are blocked out. Now, how do we hook them all together? A plant is kind of like a living thing, you know? It needs arteries to move materials, power, and information between all its different organs. And that's where roads and, most importantly, pipe racks come in. A pipe rack. Yeah, it's pretty much what it sounds like. A giant rack that holds up pipes. But it is so much more than that. Think of it as the plant's main circulatory system. It's carrying all the process fluids, sure, but also all the electrical power and the data cables. And the design of this thing, which looks so simple, is governed by some incredibly strict rules. So why so many rules for a simple rack? Well, it's all about planning for the future and planning for failure. Leaving 20% of the space empty might seem wasteful now, but it's a lifesaver when you need to expand later. And putting the pipes with corrosive stuff on the bottom level? That's just common sense. If it leaks, it just drips on the ground, not all over everything else below it. It's all about thinking ahead. Now let's look at how these racks actually get arranged. This is what's called a comb-type layout. You can totally see why, right? You've got that main pipe rack running along the bottom like the spine of a comb, and then smaller racks branching off to each process unit. This design is great because it means you can shut down one unit for maintenance without messing up the flow to all the others. And for the really big industrial complexes, you just scale it up to a double comb. Here, you've got units branching off both sides of that main central rack. It's a super efficient way to organize a ton of different processes that are all being fed from one central corridor. But what if your process units can't be shut down separately? What if they're all just parts of one big integrated system? Well, that's when you use a U-type layout. In this case, the physical layout is telling you the story. These units are so interconnected, they're basically one giant machine, and the pipe rack physically ties them all together. Okay, let's zoom in one more level. We've gone from the whole site to the arteries connecting the blocks. Now let's go inside one of those blocks, the process unit itself. This is really the heart of the whole operation. This is where the magic happens. Inside the unit, the name of the game is efficiency. You want to arrange every piece of equipment to make the pipes connecting them as short as physically possible. And this isn't just about being tidy. Shorter pipes mean you need less energy to pump stuff through them. And if those pipes are made of some crazy expensive metal alloy, well, shorter runs can save you millions of dollars. But before you can place anything, you have to know what's flowing through it. Are we dealing with something super flammable or something pretty stable?
Engineers have this key distinction: low flash stocks, like gasoline, which are really volatile and dangerous, and high flash stocks, like heavy oils, which are much more stable. That one simple classification changes a whole bunch of safety rules down the line.
So, laying out a unit is this constant balancing act between making it work well and making it safe. You want to arrange the equipment to follow the natural flow of the process, maybe even use gravity to move liquids and save energy. But then you have these strict safety rules, like keeping those fired heaters at least 15 meters away. Process logic says put it close. Safety logic says keep it far apart. The final design is always a compromise between those two. And that brings us to our final section, and honestly, maybe the most important one. All of these rules, all of this careful planning, it all has one ultimate goal: designing a plant that can handle a worst-case scenario. It's all about building in safety from the very first sketch. This means you have to think like a first responder. Can a fire truck actually get where it needs to go? The rules say your access roads have to be at least 6 meters wide. If a pipe breaks, can you stop the flow of fuel? That's what isolation valves are for, and you put them a safe distance away. And if you need to shut the whole thing down, like right now, that's why you need at least 2 remote emergency shutdown stations, located far away from each other. Then you have the hard and fast distance rules. This table shows just a few. The control room, where people are actually working, has to be at least 15 meters from the process equipment. But a security fence next to a highly flammable unit, that needs a 60-meter buffer zone. That space is there to protect the outside world from whatever might happen inside. Here's another one of those crucial numbers: 20,000 square meters. That's the absolute maximum size for any single process unit area. Why so specific? It's all about containment. By limiting the size of any one unit, you limit the amount of potential fuel for a fire. It helps stop a small problem in one area from turning into a massive plant-wide catastrophe. The key thing to remember here is that every number we've talked about, 60 meters, 15 meters, 20,000 square meters, they're not just pulled out of a hat. Every single one of them is a lesson, often a lesson learned the hard way, written from decades of real-world industrial experience. You can think of every rule as a scar from a past failure, now built into the DNA of the next generation of plants to make them safer. At the end of the day, the perfect plant layout does 3 things really well. It's efficient, so it saves money and energy. It's safe to operate and easy to maintain, which protects the workers and the environment. And it's ready for the future, with space already built in for new technology and expansion. So that chaotic mess of a refinery, turns out it's not chaotic at all. It's a highly ordered system, a beautiful machine meticulously designed for safety and efficiency. And that kind of makes you wonder, right? Now that you've seen the hidden blueprint here, what other complex, chaotic things in your own life, from the way your city is laid out to the circuits inside your phone, might have a hidden order you've just never noticed before?